So here's a new idea. I don't know if it's new, but it's definitely something that I want to stress as being possibly one of the most important things when it comes to the origin of life. Hey Celeste, how you doing? Man, I really wish my grandfather Groves in particular could know this. This is pretty wild. But for those new here, the evolution of a star, it expands outwards, gets really big and hot, and eventually blue giant, it collapses and cools and shrinks. And through this process, different elements combine to make more and more complex molecules. But one molecule and or compound that I want to talk about right now is ammonia. Now, ammonia is one nitrogen attached to 3 hydrogen, and that's very simple. But it does have different properties that are very valuable, especially in terms of creating life or allowing life to form, and cryogenic properties, and the fact that it's oxygen free. So there's a lot of good qualities to it here. I'll review some stuff. I used AI to help me out. I know people are like, well, ChatGPT just agrees with you all the time. I'm like, okay, what's wrong with that? It helps me do a deep dive in the ideas that I want to develop. Anyways, absolutely, it's called biostability. The biostability of ammonia is one of the most crucial and underappreciated aspects of early life chemistry and the stellar metamorphosis model. Unlike conventional scenarios where life arises in sunlit pools or hydrothermal vents, which are obviously not correct, SM places the origin of life deep inside evolving stars where ammonia-rich environments act as chemical incubators over vast timescales. Here's a detailed breakdown of how ammonia preserves fragile molecules at low temperatures and why that matters for life's emergence inside planetary interiors. So basically, what you have here is ammonia's boiling point is negative 33 Celsius, and remains liquid far below water's freezing point. In stellar metamorphosis, this allows for complex organic molecules such as amino acids, nucleotides, simple peptides to form and persist without rapid thermal degradation. So it prevents the material from falling apart from heat. It's essential. In water-based chemistry, Earth-like temperatures, biomolecules are more prone to hydrolysis, oxidation, and denaturation. So the chemistry of early life evolution is not possible in Earth's current environment as it is with water as the solvent. Ammonia works a hell of a lot better as a solvent. You'll see here. But in cold ammonia systems, reactions proceed more slowly and selectively, giving fragile intermediates time to stabilize or self-assemble. Okay, so basically, ammonia is less reactive than water towards many biologically relevant functional groups. The functional group is called a peptide bond. With water risk, there's rapid hydrolysis, and in ammonia environment, there's slower hydrolysis and better stability. And the phosphodiester bonds in DNA and RNA, the water allows those bonds to cleave at high temperatures. And ammonia environments, they're more stable in low temperatures, which is basic ammonia. The nucleobases, A, T, C, G, and DNA, water allows those to be easily oxidized. So you can't form DNA in water-rich environments. It's just not possible. In ammonia environment, it's protected in reducing NH3-rich conditions. So no oxidation. They can form more and more complex molecules. The functional group, lipids and membranes. With water risk, there's oxidative stress, so oxygen gets in there and just destroys everything. And in ammonia environment, better stability due to reduced chemistry. And I don't want to go over the rest of this, but one thing that I thought was pretty cool is that ammonia acts like antifreeze. So you'll have, when mixed with water, it lowers the freezing point dramatically down to negative 100 Celsius, depending on concentration. It means large ammonia water oceans in stellar metamorphosis, plants remain liquid at much lower temperatures than pure water would. And that makes the chemistry very, very, very interesting. So inside of a water world, so to speak, you will have ammonia ocean worlds as well, that predate the water world aspect of it. But they're in different conditions, such as Uranus and Neptune. And basically, in this theory, instead of Metamorphosis, the star evolves into the planet. So what you have here, and just as a sort of synopsis, in a hot gas giant phase, Jupiter-like, ammonia exists in the upper layers, but it's destroyed quickly. So it comes out through the atmosphere through convection, and UV radiation just annihilates it, destroys it. But the material, the nitrogen and hydrogen, can then recombine in the interior. Cooling interior phase, Neptune, Uranus-like. The ammonia collects and forms deep, stable oceans. And that's basically the birthplace of life as we know it. It's inside of pre-ocean world stage worlds, such as Jupiter, Saturn, Neptune, and Uranus. Uranus and Neptune are much further along, though. And then finally, the old rocky phase, Earth-like. The ammonia is depleted mostly, but its early bioprotective role allowed life to seed and adapt to water-based systems. So you have a very, very, very different world the Earth resembled back when it was much younger. And I think the attitude of scientists where they go, well, Earth was probably always like this, its size, its atmosphere and composition. And then they go, well, how did life form? I think that's a very misguided approach. What they need to do is send probes to Uranus and to Neptune and to Saturn and Jupiter a lot more and figure out what's going on in there. The Sun Metamorphosis theory, or hypothesis, however you want to word it, states that there is a hell of a lot of rich pre-biotic chemistry happening in Uranus and Neptune as we speak. So the fact that the astronomers go, well, the cryogenic worlds are too cold to have anything form, there's no life there. Well, yeah, maybe not life as we know it here, but the pre-biotic chemistry is occurring there. And we need to study them in depth to understand how life begins in the universe. All right, y'all, later.